now let's tackle the topic of this event, and we will be talking about deep reinforcement learning, which is an emerging technique which is pretty hot at the moment, and which is producing a number of results, most of them preliminary, in a number of fields spanning from robotics to finance to the management of business aspects, and we will be discussing one of those, namely inventory management. Before getting down to and going into the very topic of this seminar, let me tell you something that I'm quoting very often this year, because this quotation is fairly recent, and it is from Sergey Brin, who is the co-founder of Google, who candidly admitted of being a non-believer in artificial intelligence. And he said that since he has been training during the 90s, he was used to think that artificial intelligence doesn't work. And now he says that there is a profound kind of revolution into the field and into the technology, and the new things are emerging. The question for us, though, is what is really new? Let me mention one example without telling where, but that has been a business contact of mine, and I have been told by people that they were very eager about trying an approach for a particular application using logic programming. I've been using logic programming for quite a while during the early 90s, more than 27 years ago. And, well, they are trying that now. Good luck with that, because at least in my limited knowledge of the literature, I don't know what emerged recently which could allow us to think that by retrying something which has been tried by and large in the past, we could score a better success. So in a certain sense, we are in the presence, at least in my opinion, of a sudden change in the technology that has to do with artificial intelligence. But from a business point of view, not any less from a research point of view, we need to be very keen and very focused in understanding what actually changed and what was there already. Because otherwise, there is a saying, I think this is from Santayana, whoever doesn't know history is prone to repeat it. So we could be repeating over and over the same kind of approach with limited success. So let's try to discuss this topic of today, reinforcement learning and then deep reinforcement learning, from the point of view of what changed, what is really new. Because I think that this is fundamental in order to understand what chances we might have to score success right now in particular applications. Reinforcement learning is by no means something new. The fundamental book about reinforcement learning dates back to, by Sutton and Bartow, dates back to 1998. So by no means the fact of proposing reinforcement learning now is something that can be deemed a novelty, and actually was there since quite long. Why did not people use it? This is a question that we will try to address during this. But before going in depth and before telling you why I think that something changed, we need to go over very quickly about the theory of reinforcement learning. Actually, I think we are all used to equations and kind of things. I will not be trying to steer clear of them. I will be presenting things, but fear not. We will be just seeing equations in order to get the intuition, not in order to have a full derivation of things. But in particular, what makes reinforcement learning particularly attractive, and the marriage with deep learning techniques with having a substantial potential for improvement, is something which is very well buried into the mathematical model. So if we don't go inside it, we might not be appreciating what the technique has to offer. The basic idea is not particularly difficult to grab, and it is based on a model that envisions the presence of two fundamental components. One component is an agent, and the other component is an environment. The agent takes actions, and the environment may change its state with respect to the environment. And then there is a reward, which actually is not part of the environment, is something, let me clarify upfront, is a design tool. The designer uses the design of the reward in order to make the agent learn what is going to be the best behavior, the optimal behavior ever. But what the environment gives back to the agent is a definition of a state. Here we need to be clear, because we don't want to simulate omniscient agents knowing everything about the state. So the state that is fed back to the agent by the environment is not going to be the whole story. It's only going to be the observable part of that state. If you are a robot, you cannot have the map of this room. You can only have the set of pixels that are coming from your camera, perhaps your synthetic eyes, or other kind of sensors that the robot is supposed to be equipped with. So, in a sense, you are not going to have the true reality about the environment. You are only having those parts that are captured by your sensors, and your sensors may introduce artifacts, may introduce noise and things of the like. So whenever you see state in this case, you will have to understand that these are actually observations rather than states. What is observed by the agent. Let me also make one point remark, actually, one point of difference with other machine learning techniques, because in the broader classification, supervised learning, unsupervised learning, reinforcement learning is none of the two. It deserves a different category. And the main difference is precisely this. Let me mention an example which comes from finance. Suppose you are a small investor that is trying to understand what is the trend of stocks in order to understand whether you want to sell or buy, or even something very new. You are going to invest in bitcoins. Is that the moment of selling or buying, right? In that particular case, given the huge amount of money which is around, and if you are a small investor and you have just a very, very, very tiny amount of money available, you can safely assume that your actions are not going to influence the trend. So what you want to learn, and you might be using, people does it, might be using machine learning techniques, is learning a trend over a curve that is supposed to work independent of your actions. But with reinforcement learning, things are completely different. You assume that your actions are going to change the story. In particular, if you are managing your own inventory, magazzino in Italian, you are going to change your behavior, the story, and everything that develops from that point on. So it is a completely different story. Second part, the data set. Normally, when you have an application that is for machine learning, at the very, very first question that you ask to your customers or to your problem, if the problem can answer that, is, where is my data set? And with reinforcement learning, we normally have to tackle problems in which the dataset is non-existent, in the sense that the agent has the task of learning by doing. It collects its own data, and it learns from the data it collects. And as we will see, there will be at all times a tension between an exploration part and exploitation part. Exploitation means exploiting the kind of data you already got, and exploration is collecting new data. Should I stay with what I got so far, or should I collect more data? And what is the most effective policy for collecting those data? These are fundamental and crucial problems for reinforcement learning, which are very specific, in my opinion, to this particular technique, and can hardly be found in other situations. The very first definition that we need to make is that of the Markov decision process. Look, the model of reinforcement learning is really neat, nice, and it has a few marvels in it, but it is very prescribing. So, at the beginning, the setup is that, and take it or leave. So, actually, you need to fit your problem inside this kind of framework. The framework is pretty broad and not so constraining in a sense. It means that the environment has a set of states. In most cases, the set of states is finite, but this is hardly the case with real-world problems. In particular, with finance, you can discretize everything, but you have prices that are continuous, almost continuous, and you have actions for buying and selling that sometimes can be deemed to be discrete, sometimes they couldn't. And so you have different quantities that might be continuous as well. And the set of actions, well, in this particular case, the case of example we'll see in a second, the set of actions is finite and discrete, but this is not to be taken for granted in all cases. Of course, we will be discussing as the beginning just the two situations like this as being discrete and finite. Then there is a reward function that in this simplification only depends on the state. And then a transition probability distribution. But before going any further, let me explain this. This is a great world, and the agent, like this dot, the red dot, is supposed at any given time to be in a particular state. The state is the couple of coordinates that determines a particular box in the grid, right? So in this case, the agent will be in 0.13, or 3.1 actually, because it is y. So that is going to be the state, and that state is supposed to be observable to the agent itself. The map is not known to the agent, neither is this set of numbers, and this set of numbers are the reward. So if I am moving from here to here, say, I will be getting a reward of minus 0.02. Whereas if I'm getting here, I'm getting a reward of minus 1. Negative reward is exactly what the intuition suggests to you, in the sense that this is negative reward is a pitfall, and moreover, in this particular example, this is an exit state, because your game will be over and you will be getting a very negative reward. Whereas this is the goal, which has +1 as a reward, and it is an exit point, and the agent has to learn the exit point. So in a nutshell, the agent could be put in any of these places, and the agent, has to learn a particular policy that will allow it to reach the goal safely as possible, and trying to steer clear of the pitfall. But here comes the question. If the agent was acting deterministically and the outcome of any of its actions is deterministic as well, how come that the agent could be so stupid to fall into the pitfall? And here comes the idea of the transition probability. In this model, there is a random component which is entirely about actions. So the agent assumes to take a particular actions, and it expects a result, but it is not certain. And this transition probability accounts from the dynamic of a system which is not entirely under the control of the agent. And in the case of the example, I'm not showing this, there are slight probabilities that whenever the agent wants to go, say, in this direction, it will slip in either of those. So by being here and wanting obviously to go upwards, it might be that the agent goes on its left and then bounces back because it bounces into the wall, or it slips on the right, and that is going to be a disaster, because in that case the agent will enter into the pitfall. And this is the idea of the transition probability. Then there is a discount factor which has only mathematical relevance, and we are going to see next. The very fundamental aspect, fear not, this equation is equations of this kind are fairly difficult to manage, but they are intuitively clear. The very basic element of reinforcement learning is the definition of this equation. This is an equation that attributes a value, scalar value, to each state in the environment, observable state, of course, in which the agent is supposed to be in. So in this case, we have this guy, which is S, which is the current state, and this is the notation of V, following a policy P. What is a policy? Suppose that the agent has a deterministic policy, so it, the agent, at any given time, it decides a policy which depends on the state and on the state only. So the agent observes the state. It doesn't care about the past. It doesn't care about which time is. It just selects that particular action depending on the state. And this is the kind of thing that emerges. And look, this is the state at time t, which is supposed to be the starting time where the agent is in state S. And here you see st plus 1, st plus 2, st plus, and this is a series which might go into the infinite. And this is the kind of reward that the agent gets for entering any particular state. This is very strange, but this is also the beauty of the model. I'm not trying to evaluate the immediate return of a particular action. My model is based on the infinite temporal horizon of the entire strategy I'm being playing, right? And therefore, there is something that seems at first glimpse to be non-computable, because this is going to be, in many cases, an infinite series. There are chances for the agent to be, even in the great world, even in the simplest examples, there are chances for the agent to be spinning around pointlessly, right? And to be spinning around forever. So how can we compute anything like this? Even worse, these are not states. These are called random variables because they describe a situation which is a priori not known. Because if there is a probability that each action will take the agent adrift, away from the strategy, away from the place it would want to be, it might be that this kind of drift continues on, and therefore the farther you look into the future, and the less you will be certain about where you are. So this kind of thing seems to be just a mathematical exercise, but without any particular aspect. Let me just mention what is gamma. Gamma is a discount factor, and is something that sometimes is explained in non-technical terms as being, as in finance. Suppose you lend €1 to one person. You lend €1 and the person is going to give it back tomorrow. That is one thing. But suppose that the person is giving you back the euro in 1 year, 365 days. Everybody will tell you that your capacity to spend will be reduced. So gamma is going to take into account the fact that the money that you can get later on, the later you get the money, the less value you have right now, because you need to wait more time in order to get the money. And this is one explanation, but this explanation is about the application of the model. The true mathematical explanation is that if you use this guy, this is a geometric series, this series, even if it goes to the infinite, is bound to be this thing. So this is the value of such a series of coefficients, and suppose that you multiply those coefficients by a reward. The only constraint that you need to apply to the reward is that the reward must be bounded. There will be no infinite rewards for entering each state, which is a very simple kind of requirement to be satisfied. And therefore, this entire thing says that in actual fact, and this is its first step towards computability of this expression, which looks awkward, this entire series is going to be dominated, is going to be finite, right? Regardless of how long it is. But then, I'm not going through these mathematical procedures. If you trust all the steps, otherwise the slides will be put on the web and you can derive things and check things yourselves. If it is wrong, please drop me a line. But anyway, this kind of equation becomes a recursive equation. So actually it tells me that if I knew the value of the value function, sorry for this kind of mismatch, but if I know the value for all the reachable cells in a particular state, I could compute the value in that particular state. So knowing the value in the neighborhood tells me, the reachable neighborhoods tells me which value I should have here. This is clearly a recursive equation, but you know, if everything is discrete, this is a summation. So overall, this is a linear equation. Being a linear equation, if you have a certain number of states and you have an equal number of variables, that becomes a system of linear equations. It might be huge, but it is solvable. Therefore, what happens? It happens that in the line of principle, if you know everything, if you know every ingredient of that Markov process which I've been describing previously, in theory, but also in practice, perhaps it could be not so convenient to compute. But in practice, you can compute such a function. And therefore, you have the possibility to compute it not without a certain difficulty. But this is for a particular policy, because P in this case is a particular policy. And who decided the policy? Well, that is one policy, but we are not interested in one particular policy, because that particular policy may come from our prejudices and could be suboptimal. We would like to have the optimal policy ever. And this is obtained by maximizing this particular equation in each state with respect to the policies. Ouch! Another thing which seems completely unsolvable. How can I make an optimization over a policy which is a strategy, which is a function, right? I need to optimize a function. Well, there are techniques, of course, but it is not so easy to do at the very first. But actually, by having this kind of further type of developments, we have the same equation, which is recursive, allows for some kind of solution, which unfortunately in this case is not directly computable, because it has an exponential explosion, which is this. So this is the set of possible strategies in the case of finite variables. However, we have an expression, and perhaps we can compute it in another way. And there are methods which are incremental, I'm not showing, but methods that are, is called dynamic programming in some contexts, in other contexts, they are called iterative algorithms, put simply. But actually there are algorithms that could compute this kind of thing in finite time, and actually without that particular effort. So, in a nutshell, given the beauty and the niceties, of course we just scratched the surface of the model, but given the beauty of this model, what we have is that we can compute in theory V star. And from V star, we can compute in this way what is the optimal strategy. Let me show you in the case of the Greek world. Suppose you start from here, which is the set of rewards, and then you apply one of those iterative algorithms that I've been telling you, and at the end you have that this algorithm has a fixed point, a point in which there are no further changes, which is exactly V star, and V star with approximation of 2 decimal digits is exactly this. Then what you do? Well, actually you try to climb up. So here, where you go, here, not for sure, here, not for sure, you go over there. Why? Because there is the highest V value. So your strategy is this. And this is no surprise, because I don't think that anyone could think otherwise. But the little surprise, or not so surprise, but the little outcome that this particular example tells us, that in this particular state, you see, it is convenient, according to this algorithm, to take the long road instead of running the risk to go the shorter road, but which is riskier, because you have a much higher risk of falling into the pitfall. So actually the resulting strategy is this. And this is a map that can be given to the robot, and regardless where the robot starts in, it will be using this kind of strategy, and the model tells it that the robot itself has the maximum kind of return, so that has the best chances, according to the probabilities that we have defined in this model, to reach safely the goal state in the shortest possible time. So on the average, this is going to work. But given that we have a random phenomena, the only thing we might be hoping for ourselves, or what the robot could hope for itself, is having this kind of thing in the average, and not in the, take a seat, Jenny, and not in the directly. You can take this. There are a number of limitations in this particular strategy, because, well, in order to apply such a method, you would need to know everything about the environment. For instance, you would need to know the map. But the map is not directly, or might not be directly observable by the agent. So perhaps the map is not known to you. But even worse, there is another problem that is well known to whoever has to do with robotics, but it could be clarified in a second, even talking about finance. Do you know what is the transition probability of your actions? Hardly so. Let me mention one example which is trivial and the other one which is more artificial. Take my arm, I can grab these keys, right? Do I have the complete model of the dynamics of my muscles and the skeleton and everything? Do I have the differential equations that are solving these things so I can know when I am applying some kind of stimulus, which I'm not even aware of, that the effect that will be produced is precisely that? What I'm telling you is that if you trust me, I'm pretty much effective, as we all would be, in grabbing the keys, but I have no clue about what is the transition probability of that binds my actions at the millisecond and the effect which is taken. Suppose that you are investing and that your investment is changing the scene because you are no longer a small investor. Think of playing God in finance, of course, and betting substantial amount of money. The market will react. If you buy, the price will go up. If you sell, the price will go down, right? But with which dynamics? Are you sure that even the bigger investors are aware of that? Actually, Black, Scholes, and Morton provided a formula which says about hedging, which is a much lesser kind of forecast, and they got a Nobel Prize for that. So this is to say that mankind normally doesn't know the transition probabilities about finance, and still people is playing with finance. Well, sometimes with mixed results. But anyway, people is doing that. So that might be a way to circumvent this lack of knowledge. And this lack of knowledge passes through the usage of a particular, pay attention to this, because this is the starting point for inserting deep learning. This Q function is a different definition, but substantially equivalent to the V function, which is the value, but only it says something which at the first seems very strange. Is the value that is associated to taking a particular action in a particular state and then following a policy afterwards. It doesn't make that much sense. It is purely mathematical trick, in a sense. So the intuition doesn't help, is not particularly helpful here. But this particular function is something which is based, once again, on a recursion and a maximization and an average. Maximization of a function is an operation which can be performed, although sometimes it's very expensive. And this is, which is an average, well, or an expected value more precisely. How do you learn a particular average if you don't know the expected value? If you have a coin to be tossed and you want to know what is the expected fraction of times that coin will yield either tail or head, what do? You do experiments. You compute the average. So this guy can be learned, and this maximization can be performed. As a matter of fact, please meet a very simple algorithm, which is, in fact, the Q-learning algorithm is pretty simple to implement. The difficult part is coming to it, and the even more difficult is proving that it converges to anything. Because as hackers, we do know, the ones of you who play with computers, that we can make all the changes we want. The main problem is, will that change work? And in particular, for these kind of things, this is exactly the kind of support that the theory, however difficult as we have seen so far, provides us. And the idea is using an approximator. I think that some of you already have heard a bell ringing. In this particular case, we don't know the function Q. I use Q hat as a kind of estimator of function Q. And at the beginning, the function Q is initialized at random, completely. So it gives you random values. And then, at each step, you select you are in a state, you are the agent, you are exploring, you don't have any data, you don't have any clues, you don't have any knowledge, right? You select which action. The one that gives you the best chances according to not the Q function, which is unknown to you, but the Q estimated function, which at the beginning is initialized at random. So it's going to give you something which is not random, but is not the correct answer either. Still, you will be taking that particular action. Let me forget this probability 1 minus epsilon for now. Then the agent is in state S prime, because something has happened, and what the agent does is it updates not the Q value for the function of the state in which it arrived, but the Q value from the state it started from, and with the action which has been taken. And this is the formula for updating things. Now comes this part, which is now with probability 1 minus epsilon, otherwise select A at random. I told you that we need to strike a balance between exploitation and exploration. Exploitation is I'm taking the maximum advantage from the information I already got. And exploration is I'm getting new information. And this is exactly what is done here, because epsilon is usually much smaller than 1. It has to be smaller than 1, but it is much smaller than 1, say 0.001. And most of times you rely on the information you already got, and you select this kind of action, the one that according to your information is the best one. But with probability epsilon, so a tiny degree, you will be acting at random, i.e. exploring new possibilities. And is this strike of the balance that tells you that there is a guarantee. I'm not losing time now in telling you which kind of guarantee we have, but this algorithm makes the approximator tend to the real optimal Q star function. So in theory, you can learn the Q function, hence you can learn the optimal policy according to the Markov decision process that we have been introducing from the beginning by using this kind of algorithm. Sounds nice. It used to be known since 1998, actually much before. So if it is so nice, how come that people is not using that and throwing away anything else? The main problem is that there are a few catches that limit substantially the effectiveness in practice. So the model is sound. But if you try to apply, I better pause the keys because my example is over. I'm telling to myself. If you are working in practice, the model, however sound, does not give you the results and the outcomes you expect from it. The very first part that has to be considered is that, well, what happens if you have a continuous state? How many of these values you are going to get? It is impossible. You need to discretize in order to apply in practice this kind of algorithm at face value, taking this. So only discrete action spaces and discrete state spaces can be considered, and hopefully not so large in size. Otherwise, this kind of algorithm is going to be very cumbersome to compute. But still, there are other problems, and another problem is that at each step, you have to perform a maximization. Whoever is into the computation of maximizations, even discrete spaces, could tell you that this is not going to be a piece of cake. However, this is something that has to do with computational aspects. But there is another part that it is fundamentally related not to each individual steps, but to the algorithm as a whole, is that in practice, such an algorithm requires a huge amount of steps. It is a very, very, very slow learner. So you might end up performing millions of steps and having an improvement over your estimator, which is very limited. In the long run, in the infinite, with infinite time, should you wait for that, you have the guarantee of getting the answer, but in practice, you don't have it. And this is, of course, is the main limitation of this kind of thing. Deep learning. So far, we have been discussing things that were already in the literature. You could read them and have an idea. Now we are trying to insert into this picture something which is the new ingredient that changes entirely the picture itself. And this item is deep learning. Deep learning is another thing that, well, it has to be described with a certain degree of detail, because it's not so easy to understand and to describe. But, well, it has to do with so-called neural networks. You will see for a while still around diagrams of this kind, which are usual for neural networks, but actually the real expression is linear algebra, because neural networks by and far are linear algebra. Everything else is just a diagram, which is a nice thing, which is useful for explaining things, but is not so useful as a whole. But anyway, you think you have an input layer, and you see here you have a vector, because your state of things observed, state, are we already talking about reinforcement learning? Your input, let's stay very neutral at this point. Your input may contain several variables, so they can be arranged in the form and the shape of a vector. And here, for simplicity, I have just one unit, meaning that the function we want to synthesize, this guy, is a scalar function. It might be a vectorial function, it doesn't matter. But what we have in between is a set of units, so-called, which are the hidden layer. Well, if you see from the linear algebra perspective, you take the vector x, which is this, and you multiply, you apply a matrix to it, and once you have a matrix of some sort, what happens usually is that you have another vector, because a matrix is nothing but a linear transformation of a vector from one space to another space. So you get another vector. In this case, you have a vector of 4 elements. Then you apply a nonlinear function of some particular kind. There are more frequent functions like the sigmoid, the hyperbolic tangent, or other functions, but they need only to belong to a particular class in order for the result, which I'm going to tell you. And then you make the last step, which is this layer. You multiply this vector. Usually these functions are scalar, but they are applied element-wise. So they are applied unchanged to each element in the vector, which is the result of this operation. And then you multiply scalar product with another vector, which is the final thing, and you get a scalar value. What's the point in it? There is a theorem, which is long known, that tells that any function, actually I need to be more precise, any continuous function in a compact subset, but anyway, any function y can be arbitrarily approximated by a guy like this with an arbitrary degree of approximation. You only need to know the parameters, and the parameters in this case are this w, which is the matrix, this is the input, this c, which is a constant but is a vector, this w, which is a vector again, and this c, which is another value. If you happen to know those values, the right ones, you can get as close as you want to any functions, provided that if you want a very high degree of approximation, you must increase the number of units or the dimension of this at the hidden layer. So you need to grow the blue layer in order to have a better precision. But still you can get it, right? Well, deep learning comes from the fact that people have tried to use networks at a higher level of depth. And here we see 2 layers, and here we see 3 layers, and this is the corresponding expression. But actually this is something that raises doubts. I mean, I already have the result that with just 1 layer I can have an universal approximator. Why increasing and having more layers in the network? Well, there is another formal result. Actually, it's not so neat, it's not so precise. So it is result plus empirical evidence that whenever you have several layers, what you can get is a better utilization of your units. So you grow linearly in layers, and it is equivalent to a growth, an exponential growth in units in just 1 layer. So it is very effective to layer to have several layers of this kind of thing. And you know something? This fact was already known not so long ago, but by no means it is something very new. What the real novelty, and we don't have time to go in depth into this, is that it was known since long that it was a real nightmare to try to find the parameters, for all these layers from data. Because usually what these kind of things, neural networks as a whole, not recursive one, feed-forward neural networks like the one depicted here, are just function approximators. They don't do anything else in their whole entire lifetime. Only you need to learn the right parameters. And the only thing normally in practice that you have for making the network learn the parameters is by having an example. Actually, by having a huge amount of examples, having a data set from which you can derive the right parameters. And you know what? Whenever you have a very deep network, the learning process of parameters becomes a real nightmare. Skipping a number of details, they discovered how to do it. And this is something that started back in 2006 and exploded in the last, say, 3, 4, 5 years. But in my opinion, the fact that they learned how to train deep networks is, don't tell anyone, the only novelty that appeared in the field. Then there are a number of things, and we are going to see one about deep reinforcement learning, that are changes, that are provoked, that are caused by this apparently very local, very specific kind of change which occurred in the field of neural networks. Plus, there is something else. Nowadays, and I'm talking about the system TensorFlow, which has seen its initial release, RC, Release Candidate 1, back in March 2017, so it's not even 1 year old, right? Which is something which is very convenient if you work in the field, because most of these tricks, and it is continuously updated because it is updated by Google and is a way for marketing for Google, I'm saying in the most neutral sense and not taking any stance here, is trying to feed into this implementation all the tricks and all the novelties so that you don't have to bother, you just use the tool, TensorFlow, and you will have everything you need in order to take advantage, to exploit actually, these developments, these new things in the field of deep learning, and in particular for training from huge data sets. Still, we didn't clarify how the two things, reinforcement learning and deep learning, can be matched together to produce better results. And this is exactly the next step in our talk. So actually what we have left, and this is exactly the same slide you have already seen, is that, or at least for the algorithm, the fundamental aspect of the Q-learning algorithm is having an approximation. An approximator, actually, which is the approximation of, guess what? A function. Because you have as input the state, which might have several variables, many variables, and the action, which can also have many variables, right? We'll see an example later on. But at the end of the day, this function just produces a scalar. So apart from the fact that the diagrams would be much more difficult than the ones we have seen before, it is just a diagram like the other ones. And we know that neural networks have the capability to approximate any kind of function, so any kind of Q function. Now, in a nutshell, and to make a long story short, suppose that you have an algorithm that is affected by the problem that this Q approximator updated in this way is an incredibly slow learner. And suppose that all of a sudden someone comes up with a much more effective and much better learner, which is a spare part, so to speak, that you can take off the shelf and plug it into your engine. I'm talking in particular to the male population. Have you ever tried to change the carburetor of your moped or things of the like and seeing what is the result? This is something like that, because in this particular case you'll have a component which is a much better learner that you can plug into the existing algorithm. Well, this is one algorithm we have been using for robotics, things are not so simple. So I try to simplify, and believe me, the basic idea is exactly this. I'm not going through the details of the algorithm which has been applied for the experiments here, but let me just discuss a few aspects that are typical of this algorithm and will tell you how sophisticated must be the integration. It's not so simple as plugging into one part. But in spite of the complexity of the notation, the algorithm preserves, at least in my opinion, some kind of intuition which is pretty good to keep. Pretty good to keep if this guy is not frozen. Okay. Sorry for that. There has been a sabotage of this talk. Okay, we are here. We use a deep neural network for our cube, and this is something which I already announced. But in this particular case, this is the first expression. Then, actually, frozen. You see, Mirto, this is the damnation of Tutankhamen applied to this guy. Okay, let me restart this in the hope.
Are you sure to restart it?
No, not the computer. I'm sure I don't want it, and you Mirto know why. Well, not because it was your fault, of course, but actually because you were attending and you had to suffer the consequences with me, with all of us. Let me go. I'm not planning to redo it from start. We were talking about the sophistication of the algorithm, and actually it uses two neural networks for stability. One is the one which is used for immediate predictions, and the other one is a target, and the changes made in the immediate predictions are slowly and gradually translated to the target rather than making that all of a sudden, because experimentally this has proved to be a much more stable kind of attitude that can be taken. So this is not about the mathematical model, but this is very effective in practice for reasons that we are going to see. Then there is a thing which also makes it clear that making diagrams with the networks, with connections, is no longer of any use if you go away from certain types of networks, because by carefully working on the tensorial, i.e. linear algebra expression, you can construct your work, your network. I ask you to refer to the article in order to see the details, and actually it's not even so clear. Anyway, perhaps later on we will make a reading group about that specific aspect to clarify this, which is very interesting. But anyway, there is a way to arrange the expression in order for the maximization to be done automatically inside. So in this particular step, they take another component of the network, is not easily seen, but that particular component, this guy, is inside the expression, and it is a quadratic form, and it allows you to avoid the maximization. It is already performed, right? It's another of the many mathematical niceties that are used in this particular situation. And then, rather than using the epsilon and 1 minus epsilon, it uses a stochastic process, as we will see, a random walk, in order to cause and to foster the exploration. The noise which is added is going to decrease over time, but is going to introduce some random components into the action, so the agent will be forced to explore and not to exploit blindly the kinds of information that it has acquired so far. So in a certain sense, the exploration component goes here, but there is another nice aspect, which is this. Suppose you are trying to learn a function. I'm not going into the theory, but one fundamental aspect for the theory is that your data set must be made of independent samples. But if you are learning a strategy and you are collecting data as they come in, they are by no means independent, they are temporally correlated. Why? Suppose that I'm here and I'm collecting data. I wish I could have the teleport, so in the next step I could be on the other corner, but this is not the case. So the next steps will be here or here, they will be close. So there will be a strong correlation between the situation here and the situation, say, in the few instance. And therefore, what does the algorithm? It uses a replay buffer rather than using the data collected as they come in order to train the approximator for the Q function. It stores everything into a big, possibly a big buffer, so all the values collected so far, and then when it comes to train the approximator, it collects a mini batch which is sampled at random from that particular huge replay buffer, and it trains the network on that kind of situation. But this happens online. So at every time, at every step in time, what happens is that you have some kind of playing, you play something, you get the results, and then you update your network. You train the network a little bit with one or more mini batches. So it is an ongoing and always ongoing kind of process that takes place, but which in the end becomes particularly effective. And, well, there is something else which is an extra bonus, which is extremely interesting for anything which has to do with robotics, with autonomous driving or things of the like. You don't need discretization anymore, because the only thing you need discretization for is for learning the Q function. Once you have the Q function, if you can maximize the Q function and the Q function tells you which way to go, who cares about the fact that the Q function is either discrete or continuous? And in this case, of course, this is not to say that discrete situations are more or less, that continuous situations are as difficult to learn as discrete ones. But in this particular case, at least from the mathematical model, there is nothing more that prevents you from having continuous action and state space, which is absolutely a good quality to have.